Okay, so the next speaker is Gregory Miermont, who will start his series of lectures on random planar maps.
Thank you very much, Nathaniel. Thanks a lot for the invitation. It's a great pleasure to be here. The topic of this course is this series of lectures is going to be about random maps. And somehow the motivating question for studying such objects is the following vague question, which is, what does a surface look like if its metric is chosen, say, uniformly at random. Let's say at random, maybe. Okay, so of course it's a very vague question, but you can, for instance, take the sphere. So we all have the idea of the round sphere, but as we know, we can put various metrics on the sphere, say Riemannian metrics. Okay, and so what happens if you choose one of these metrics at random? So the problem is that if you ask the question in this way, it doesn't really make sense because there is no nicely defined, Lebesgue measure on the set of Riemannian metrics that has the invariance properties you would like, because this set is too big, it's infinite dimensional. So in order to attack this kind of question, which by the way is in the beginning motivated by theoretical physics, so in the theory of two-dimensional quantum gravity, the idea is that gravity, I'm not at all a theoretical physicist, so not exactly sure of what I'm saying here, but gravity is the theory in which you want to describe space-time, by a manifold, okay, by a geometry on four-dimensional geometry, as we know. But and in quantum gravity, you want to understand the very fine structure at very small scale of gravity. And one way to interpret that is that you can imagine that this geometry fluctuates randomly around a kind of a ground state. And it turns out that if you try to do a consistent theory of four-dimensional quantum gravity space-time, it's something extremely difficult, and nobody really has the knows how to do that. So physicists have been interested in playing with toy models, and one toy model is to consider just two dimensions, which are two dimensions of space, and to understand what's a fluctuating two-dimensional geometry, a random geometry looks like. And that's somehow the motivating question for this, the motivation for this question. Okay? But again, this question is really ill-posed, so you have to do something about it, and there are actually several ways to try to attack this question mathematically. And the one I'm going to be interested in is a discretization of this problem. Okay. So in order to make an analogy with a situation that is more common to probabilists, you can ask the very same question, say Q prime, what does not a surface, but now a random path, okay, look like if it's chosen uniformly at random? And of course, the natural answer to that is really Brownian motion. And there are, if you understand paths as being continuous paths, and there are various ways to decide that Brownian motion is actually the right random path chosen uniformly at random. But one way that is maybe the first thing that you never learn in the beginning that before actually, okay, if you do a first course on Brownian motion, maybe you've learned that it's a continuous process with Gaussian increments that are independent and so on. But if you want to get an intuition of what it is, you start by looking at random walks, okay, and then somebody tells you that actually the continuous counterpart of random walks is Brownian motion, okay, and it's actually, I think, the most intuitive way to look at Brownian motion. You take a simple random walk. Okay, so it's if you like, a discretized random path. Take a simple random walk, and renormalize it diffusively. Okay, so say maybe you look at simple random walk at time nt and divide by square root n, and you know that this, as a random path, converges in distribution as n goes to infinity to Brownian motion. Okay, so somehow Brownian motion is the natural continuous random path, but there is really more to it, because you could say, okay, but what about other random walks? And as you know, as soon as the random walks you consider are centered and have a finite variance or finite covariance matrix, maybe a scalar covariance matrix, then Brownian motion is still, you know, the limit. So Brownian motion has, of course, this universal character to it. So it's a very robust object that arises as scaling limits of various discrete objects. Okay? So the motivation about random maps is to do the same thing but for surfaces. Okay? So what you need to do first is to think about what the natural analog of discrete paths should be, and this analog is maps. Okay, so here the idea is that maps are natural discrete analogs to metrics on surfaces. Again, of course, this is still very rough. So what is a map? So definition. So a map on a topological surface. So let me take a topological surface. Essentially, you know, if you ask that this surface is connected, compact, without boundary, orientable, and so on, you don't really have too much choice. Okay, it's either the sphere or the torus, or a connected sum of two tori, or a connected sum of as many tori as you want. Okay, so this is really here the sphere, here the torus, here somehow the surface with two handles, and so on. Okay, so in fact, in essentially all of the lectures, I'm just going to consider the case of the sphere. In this case, we talk about planar maps or spherical maps. But at this time of the lectures, it's good to keep a little bit of generality. Of course, you could also consider non-orientable surfaces, and there is also a nice theory for non-orientable surfaces, but it's more complicated. Okay? So a map on a surface S is an embedding of a finite graph in S, such that the connected components of the complement of the embedding are homeomorphic to disks. Okay, so maybe I need to explain a little bit some of the terms here. So what do I mean by an embedding of a finite graph? Well, so by embedding, I really mean that the graph, let's say G equals VE, is represented by a collection of simple paths, which I want to call the edges, with extremities, so let's say whose extremities are the incident vertices. Okay, so it really means that for every edge of the graph, so let's say we want to represent it in the sphere, for every edge of the graph, I consider a simple path that represents this edge, okay? And the extremities are the adjacent vertices in the graph structure. Okay, so it's if you like, a particular representation of the graph, and you should be careful at this time that not every graph can be represented in a particular surface. Okay, we are going to come back to that in a second, but very well known, for instance, that the complete graph with 5 vertices cannot be represented embedded in the sphere. So why is that? It's really because, okay, so I didn't finish the definition here. I really want the edges to be disjoint, except maybe at the extremities. Or if you prefer, it's not very well formulated, but the relative interior of the edges, so the edge minus the extremities, are all disjoint, pairwise disjoint. Okay? In this case, I consider that as an embedding. So what I really forbid is that 2 edges cross like this. This is forbidden. Or if I really want them to cross, then I should add this as a vertex, okay, and divide the edges. So in fact, at this moment, it's also possible that the graph, I really want to consider the most general notion of graph as possible. Okay, so it can be a multi-graph. So you could have multiple edges or even self-loops. So I also allow some simple loops. So by a simple loops, I just mean a based loop, which is a simple path, except that the extremity is visited twice. Okay, and I also allow multiple edges. So for instance, the picture that I've shown you here is not yet a map. Okay, it's certainly an embedding of a finite graph, but there is a little problem, because if now I consider the connected components of the complement of the embedding, okay, I remove the edges, then okay, these two connected components are topological disks, but then this other component here is not. Okay, it's a sphere minus 2 holes, two points, and it's not homeomorphic to a disk. So this is not a map, okay, but if, for instance, I add this edge, then this is a map. Okay, and in particular, in the case of the sphere, a map is really an embedding of a finite connected graph. Okay, as soon as you have a connected graph embedded in the sphere, then you will have this property that the faces are disks. Okay, the faces, the connected complements of the components of the complement. Okay. Okay, so this is a map. In the torus, or in higher genera, things are a bit more complicated. For instance, this here is not yet a map, okay, although it's a finite connected graph and it's embedded. Okay, and the problem is that if you remove this face, then the complement is a torus minus 1 point, and it's not homeomorphic to a disk. And the reason why is that you have paths, for instance, this path, that cannot be contracted into a point. Okay, so you need somehow a structure. The maps have to represent faithfully the surface on which they are drawn. Okay, that's really the idea behind this somehow longish definition. Okay, so for instance, this, on the other hand, is a map. Okay, you can check that now all the faces, there are actually 2 faces, one here and one here, and there are two disks. So maybe another way to consider maps, which is maybe less intuitive at first, but which maybe is in fact simpler mathematically, is so maps can also be seen as gluings of polygons. So consider a collection of polygons, for instance, a triangle, a square, 2 squares, like this, maybe another triangle. Okay, two triangles and two squares. Then what you can do is you can glue the polygons together by identifying edges in pairs. Okay, so gluing the polygons, forming a surface. Okay, so for instance, you can ask, let's say, these two edges to be glued together, then these two edges to be glued together, and so on and so forth. Okay, something like that. Okay, so with this little diagram, it's easy to construct a topological surface. Okay, if you take a point which is in this square, then you know exactly what the neighborhoods are. They are just the neighborhoods in the polygon. And if you take a point on the boundary, how do you define the neighborhoods? Well, you know what they should be on this side, and then you look at the point which is identified on the other side, and consider this. This other part of the neighborhoods, and you do a similar thing for vertices at for the vertices of the polygons. Okay, so it's certainly a topological surface, but at this point you should wonder what kind of surface you've obtained. Okay, in particular, you see that on this picture I have a crossing diagram for my identifications, and this tells me somehow that this cannot be a sphere. Okay, if you want to get a sphere in the end, then you should have a diagram of identifications that do not cross. Okay, so you can check that this, in fact, is a representation of a torus, if I'm not mistaken. Okay. So, why is it really the same? Well, you see that once you've obtained a surface by gluing the polygons, you have naturally a graph drawn on this surface, and the edges, of course, are the edges of the polygon. Okay. And by definition, the connected component of the complement of the embedding are just these polygons. Okay. So here, in fact, you could say, but can you obtain any map in this sense as a gluing of polygon? And the answer is really yes, in the sense that if you consider maps as really combinatorial objects rather than particular embeddings, then it's really the same. So maybe I should say that maps are usually considered up to isomorphisms. So we say that a map M on S is isomorphic to a map M prime on S prime if there exists a homeomorphism from S to S prime. And I want this homeomorphism to preserve the orientation. Okay, I want really these two surfaces to be the same topologically. Okay, so if there exists a homeomorphism that preserves the orientation, that sends the edges of M onto the edges of M prime. Okay, so it's if you want, it's really a graph. It's such an isomorphism induces a graph isomorphism. Okay, but it's more than that. It preserves also the structure of the embedding. Okay, and now somehow if maps are considered up to isomorphisms, then the two definitions I've given here, either a graph embedded in the surface or a surface obtained by gluing polygons, is really the same one. It's only one notion. Okay, so a couple of extra notions that are going to be useful. So, of course, so in a map, so every vertex has a degree. Okay, say every vertex V has a degree d of V. It's just the usual graph theoretic notion of degree. But now, I want to call faces of the map the connected complement, the connected components of the complement of the embedding. And I want to insist on the fact that every face f has a degree. So what do I want to call the degree of a face? So let's look at what a face can look like. So it's maybe in this, the second representation here might be better. So a face is really a polygon. Okay, so some of the edges, of course, might be identified in pairs in the same polygon, but for instance, if these two edges are identified together, it means that the polygon is really represented in this way. So you have something like that, right? Let's see, so 1, 2, 3, 4. Okay, so if you want to identify these two edges, somehow you want to glue them from the exterior side, and you get something like that. Okay, but viewed from the inside, what you see around you is still really a hexagon. Okay, for instance, if you go around the face from the interior, you really see this edge twice, one going up and one going down. Okay. So what I want to call the degree of the face f, of course, is just the degree of the polygon defining the face f. Okay, so the degree of the polygon associated with f. And another way to view that is to say that it's also the same as the number of times when you okay, it's the number of oriented edges say E, such that the face located to the left of E is equal to f. So this is the face located to the left of E. So for instance, in this picture, let's say that this is the oriented edge E, and this is f of E. Okay, and here you see that f of E is, it's twice incident to the same edge, okay, but with the two different orientations. Okay. So of course this definition is not as good maybe as the previous one, because it really depends on the orientation of the surface. Okay, in order to say when you go along an edge what is the left and what's the right, you need an orientation a priori. Okay. So once you have this notion of degree, there is another very important notion that comes with it, which is the notion of duality. Okay, so with every map M, one can associate its dual map somehow by switching, by exchanging the roles of vertices and faces. Okay, so I'm going to declare two faces to be adjacent if they are separated by one edge. Okay, so the best is to actually draw a picture. So let's consider, for instance, this map. Okay, so the dual map, so the vertex set of the dual map is going to be the set of faces. So a way to do that is to add a vertex inside each of the faces of the map. And I want to connect these vertices by an edge whenever these two vertices are separated by exactly one edge. Okay, so you obtain something like that. So maybe I'm not going to okay, it's my first ugly picture, but there are going to be many others, don't worry. I tend to make pictures that are too complicated. So anyway, okay, so you obtain a map in which, so the initial map had 3 faces, and this one has 3 vertices. Okay, and the number of edges is the same. and the number of faces of the dual map is just equal to the number of vertices of the primal map. Okay, each of the vertices, the white vertices here, is trapped in exactly one green region, if you like. Okay. So maybe the last graph theoretical notion I want to discuss here is that of the Euler formula.
So can I just ask? So you
Sure.
allow now multiple edges.
Sorry, say it again?
You allow multiple edges.
Yeah, I do. So it's actually important in this case, you know. So I have to allow loops, self-loops, and multiple edges. In this case, it just means that some faces have degree 1 or 2. Okay, essentially, well, it doesn't exactly mean that, but it implies that some faces can have degrees 1 or 2. Okay, and you see that self-loops, they will correspond exactly to these edges that are entirely contained inside a face. Okay, if an edge is twice incident to the same face, then the dual edge is going to use it as a self-loop. Okay, so I want to discuss quickly the Euler formula. So let M be a map on the surface which is obtained by gluing G tori together. Okay, so it's a surface with G handles. Okay. Then, so if I add up the number of vertices and the number of faces and subtract the number of edges, then I always get the same number, which is 2 minus 2G, so which is called the Euler characteristic. So it's really the Euler characteristic of S. Okay, it's an invariant. It doesn't depend on the graph, or actually the map that I've drawn on top of S. Okay. So at least when G is equal to 0, this formula is not extremely difficult. So maybe exercise. So, well, prove it, or at least you know, get an impression of how it goes. When G is equal to 0, so the idea is that starting from any map, you can, you know, recursively remove edges without breaking the cycles of the map until there are no cycles available. And if there are no cycles available, it means that the graph has no cycles and is connected, so it's a tree. Okay? And for tree, well, since there are no cycles by the Jordan theorem, it means that there can be only one face. You know that on the sphere, if you want there to be two faces, you need to have at least one closed curve in the graph. Okay, so there can be only one face. And it's another well-known fact that in a tree, there are always one vertex more than the number of edges. Okay, which is also something that you can prove by recursion. Okay, you find a leaf in the tree, remove it. So in this way, you remove one vertex and one edge, and continue until there is only one vertex and no edge, and you get the formula. So you see that here it's just saying that the number of vertices minus the number of edges is 1 for a tree, plus one face, and that gives 2. Okay, and then you can convince yourself that starting from any graph, you can indeed recursively remove edges that belong to some cycle. Okay, let's say this edge. So if you do that, it means that this edge is incident to two different faces. Okay, and by removing this edge, you also remove one face and no vertices. Okay, so that's in a nutshell the argument. Of course, if you want to turn that into a full proof, it takes a bit more work. So this formula, we are going to use it in places, okay? But I want maybe to discuss one nice application. So I want to step aside from the main goal, but a nice application is that, for instance, K5, the complete graph on 5 vertices, and K33, the bipartite complete graph on 6 vertices, cannot be embedded in the sphere, okay? And if you've never, you've probably encountered that before, I think, but if you've never seen a proof, then there is a very nice one using only the notions we've seen so far. So let me actually discuss this one because it's a nice, recreational problem. You have 3 houses and you have 3 supplies of water, electricity, and gas. Okay, but you live in flat land, so you can you need to bring electricity, water, and gas to all of the 3 houses, but you don't want the connections to cross. Okay, because gas and electricity, I don't know. It's okay. So, or gas, there is an expression in French, l'eau dans le gaz, you don't want that. Okay. So, okay, so can you do that? And no, you can't. So why is that? So you see that the bipartite complete graph, it has 6 vertices and 9 edges. Okay? Whatever the embedding. Okay, it's just a property of the graph. So the number of faces by the Euler formula, if you can embed it in S2, well, it should be the Euler characteristic minus the number of vertices plus the number of edges. Okay, so it's 5. Okay, so whatever the embedding, there should be 5 faces. Nothing to do about that. But then you check that there is another property of this graph, which is that there are no cycles of edges with lengths that is smaller than 4. Okay, so bipartite graph, and there are no multiple edges. So it means that if you want to go from a vertex and come back to it, you need to go across at least 4 edges. Okay, so there are no cycles with less than 4 edges. So for every f, the degree of f must be at least 4. Okay, because a face is bounded by a cycle of edges. But now let's look at the sum over all faces of the degrees. Well, first of all, we know that it's bigger than 4 times the number of faces. So this is 20. Okay. And on the other hand, when you sum the degrees of all faces, it means that you count every edge twice, once for every orientation of the edge. Okay. So this is also twice the number of edges, and that's 18. Okay. So it's a contradiction, and okay. Okay. And you can do exactly the same argument for K5 using a slightly different argument for the degrees, since you have triangles. You could have triangles. Okay, so let me take, just quickly a step back and look at where we are heading now. I was claiming a couple of minutes before, at the start of the lecture, that maps are somehow a natural discrete analog of metrics on surfaces. So there are, in fact, various ways to consider maps as discrete metrics. So for instance, with every map, we can, say on S, we can associate several natural metrics, say on S, and maybe you know, if you come from geometry, maybe the most natural thing will be to say, well, a map is just a gluing of polygons. So I'm going to put the usual Euclidean metric on each of these polygons and glue them together and look at the you know, the glued metric. It's going to be really a Riemannian metric that is flat everywhere, except maybe at the vertices where you can have conical points. Okay? And it's something actually very common to us. I mean, you know, when you know, we have all constructed, you know, witch's hat like this. You know, you roll a sheet of paper until it has a conical point. Okay, it's not something that I'm going to to teach you, right? But so this you can consider it really as a map, right? If you glue the sides of this sheet together, then you obtain a conical point. Okay, and that's really what's going on here. Okay, you obtain something which is whose geometry is flat everywhere, except maybe at the vertices. Okay, very good. So e.g. Glue Euclidean polygons. Okay, but there are also other ways to put a metric on S given a map. You can also consider just the combinatorial graph distance on the set of vertices of M. Okay? So it's not quite a metric on all of the surface, but it's if you imagine that there are many vertices, then you can imagine that they are sufficiently dense in the surface. Actually, it's not very difficult to construct an explicit metric on the whole surface that, you know, extends this combinatorial graph distance. So what is the graph distance? It's just the distance between vertices U and V is the length. So minimal number of edges needed to connect U and V. Okay? So of course, you see that these two metrics, they are actually quite different. Okay? If you, for instance, if you decide to glue these two polygons together, these two vertices in the graph distance will be at distance 2, but in the Euclidean metric, you certainly have a shortcut here. So they are not the same. But in everything that I'm going to discuss, it seems that the actual choice that you make is not so relevant. Somehow the randomness dissolves the choice that you make into maybe a local change of the metric, but not a global change. Okay, so this choice in everything that I'm going to say shouldn't really matter. But for technical reasons, we are going to choose always the second one, and you will understand soon why. Okay. Now the idea is we want to consider a large map or large random map, say a triangulation of the sphere with n triangles. Okay? And what we want to understand, let's call it Tn, and I want to understand the structure of the metric space V of Tn equipped with the graph distance. Okay? And this is somehow my model for a random discrete surface. Okay? It's not at all a surface, it's a finite space, but again, you know, it's not difficult, for instance, to extend this metric to the whole space so that it really looks the same. We are going to discuss that in a couple of lectures. Okay? So this is my model for a random discrete surface. And as n goes to infinity, what you expect, first of all, is that, you know, the triangulation gets bigger and bigger, so somehow the distances, they blow up. Okay? So what you really want to do is to rescale the distances by some appropriate factor, let's say an, okay, and we'll see in maybe in a couple of lectures, what AN should be. And we want that after this rescaling, we get a convergence to a limiting metric space. Okay, limiting random metric space. Okay, and this is somehow the goal of this lecture is going to be to explain to you how you can actually do that. But maybe the first problem you encounter when trying to address such a problem is to, well, you need to sample actually a triangulation, from the set of all non-isomorphic triangulations of S2 with n triangles. Obviously, I didn't comment on that, but large random map, I didn't say that it's really a uniformly chosen. And why can you choose uniformly a triangulation with n faces? Well, you know that you have n faces and you have to pair edges by, to identify edges in pairs. So you have obviously only a finite number of ways to do that. Okay, less than the number of permutations, less than n factorial, and in fact, much less than that. Okay, but now if you want to actually sample such an object, well, it's way better if you are able to count how many there are. Again, that's the first problem you want to address. And so maybe 2 is counting maps. And let me start with a theorem, which is initially due to Tut. So let Mn be the set of, so plane or planar maps with n edges. Okay, here maybe a little bit of vocabulary. So planar map is just means an S2. Actually, I usually say plane map. Okay, and here I want to add a little extra convention. So I want this map to be rooted, and that shouldn't. Okay, I will explain in a second what it means, but it shouldn't surprise you too much that I want something else. For instance, if you want to, you have probably all seen how you enumerate trees, plane trees. How do you do that? You start from the root of the tree, and then you look at the subtrees above this root, and then, for instance, you use generating functions to obtain an equation on the generating function for the number of trees with n edges, say. Okay, but what allows you to start anything in that process is that you have a root in the tree. Okay, you know that you can start from the root and get this recursive decomposition. If I give you a tree which is unrooted, you first have to choose where to start to decompose your tree, and that can induce a bias that's quite difficult to deal with. And actually, there are no, for instance, there are explicit formulas for plane trees, but no explicit formula for rooted plane trees, but no explicit formulas for unrooted trees. Okay, so by rooted, I mean that I have distinguished one oriented edge. Okay, and somehow this edge is going to serve as a starting point to explore the map somehow. Okay. Right. Then, let also maybe Qn be the set of the rooted and plane quadrangulations with n faces. So what is a quadrangulation? It just means that the degree of f is equal to 4 for every f. So it's just a gluing of quadrangles, of squares. Then, so the cardinality of Mn is given by the following exact formula. It's an explicit formula, I mean. So it's 2 over n plus 2, 3 to the n over n plus 1 times 2n choose n. And it's also the same as the number of quadrangulations. Okay, so a very, very simple formula. Actually, you can, recognize here in this little part the Catalan number of order n. Okay, and this actually counts plane trees with n edges. Okay, so it's quite striking that the number of maps is just the number of trees, with n edges, is just the number of trees with n edges times some very simple prefactor. Okay, and we are going to explain this, I hope, by the end of the lecture. Okay, so first of all, so I'm going to at least to indicate how you can maybe not fully prove, but understand that. So the initial proof by Tutt was using generating functions, and it's a kind of very technically involved, at least at the time it was very technically involved elaboration on the usual enumeration techniques, say for trees. And the problem of the method is that you have no idea whatsoever why the number of trees is involved here. Okay, so about 20 years after the work of Tutt, some combinatorists, so Corey and Vauquelin, tried to obtain a bijective proof of this formula. Okay, and this is what I'm going to explain to you. So first of all, the fact that Mn and Qn have the same cardinality, it comes from a very simple bijection. So if you have a map with n edges, so maybe say something like that, then you can turn it into a quadrangulation by, so it really looks like the dual construction that I did before, except that now, instead of traversing the edges, you want to connect the dual vertices to the primal vertices in this way. And you do it for every corner. Here, for instance, this vertex is really incident twice to this face. So you want to link it to the center of the face twice. Okay? Okay? And the claim is that this is a quadrangulation. Okay? And I mean, this was somehow any map. Yes?
Is it possible to use white and red, let's say, rather?
Okay. Right. Okay? Is that better? Okay. Okay, so why is it a quadrangulation? So it's very simple to see. You see that every white edge is trapped between 4 red edges. Okay, it's just somehow by definition. Okay, and the converse construction is quite easy. Starting from a quadrangulation, you take a bicoloration of the vertices in 2 colors, red and white, and then you draw all the white diagonals. And the fact that you can do that is due to the fact that quadrangulations are bipartite maps, which means that there indeed exists such a bicoloration. Of course, you could also choose the red diagonals. Okay, so how do you actually invert the picture? Well, it's due to the fact that the maps are rooted. Okay, so if you have distinguished an edge of the white map, then there is a systematic way to choose a root for the red map. Okay, so you can really invert this picture. Okay, so in order to explain why the enumeration formula is given by this formula, so I'm going to explain a bijection which is due to Corey, Vauquelin, and Schaeffer. So the Corey, Vauquelin, Schaeffer bijection. So somehow it was really introduced by Corey and Vauquelin in the early 80s, but this bijection was almost abandoned until Schaeffer, who was a PhD student of Corey, somehow reconsidered this bijection and actually revisited completely the enumeration theory of maps using this kind of techniques. Okay, somehow, I will explain in a second why, but Corey and Vauquelin were not completely satisfied with the bijection that they obtained. Okay, so how does it work? So first of all, let Tn be the set, or maybe let me use be the set of trees, plane trees, with n edges. And I want these plane trees to be rooted. And I want Tn to be the set of pairs Tl, where T is a rooted plane tree with n edges, and L is a label function from the set of vertices of T to Z, such that the label of the root is equal to 0. And for every U and V adjacent, I want L of U minus L of V to be at most 1 in absolute value. Okay, so the difference is 0, plus 1, or minus 1. Okay, so what I want to show you now is a construction that starts from a label tree and constructs a quadrangulation. Okay? So start from TL in Tn. So let me draw, for instance, this. So 0, 1, 0, minus 1, minus 2. Okay, so this is a plane tree. It is rooted. And now what I want to do is I want first to go around the tree in clockwise order. Okay, so every time, so for each corner of the tree. So what is a corner? A corner is really a little, angular sector delimited by the edges of the tree. Okay, so every vertex in the tree with degree k is surrounded by k corners, k distinct corners. So for each corner of the tree, I want to link this corner to the next available corner in contour order. Okay, so maybe each corner with label L, with label L minus 1. Okay, the label of the corner, of course, is the label of the vertex it's incident to. Okay, so for instance, starting from the root here, so I have this first corner here, and I want to link it to the next available corner with label minus 1. So I do it like this. Okay. Then I go up to this corner. I want to link it to the next available corner with label 0. So I do it like this, then back to 0, and you see that I'm going to link it to the same here, minus 1, and so on and so forth. This minus 1, I want to link it to this minus 2. And then at this point, I'm stuck because I'm at the minimum label that's available. So I want to link it to an extra vertex, which I want to call V star, okay, with label minus 3. Okay. So needs to add an extra vertex with label so the minimum of L of V for V in V of t minus 1. Okay? So I'm at this minus 2, then minus 1 is connected there, this minus 2 connected to the extra vertex. Then I'm back at this corner. I want to link it to the next available minus 2 in contour order. So you see that I have now to go all around the tree and connect it there. Then this 0 has to be connected to the next available minus 1. So again, I have somehow to wrap it in this way. 1 to 0 and 0 to minus 1. So again, it's barely readable, but and the claim is that the white graph, so the resulting graph corners to the what I want to call their successors is a quadrangulation. Okay. So maybe it's not so clear on this picture because a lot of the faces have been elongated in a kind of strange way, but you can see, for instance, that this red edge here is really trapped between these 4 white edges. Okay, the one going from there to there, and so on and so forth. Okay, maybe a bit harder to see, but this edge is trapped in this quadrangle where this edge is visited twice. Okay, so it's a quadrangulation with n faces. So I'm already over time, so I will take maybe 10-15 minutes next time to explain why this claim holds. Actually, it will be good to have another look at this bijection because it's quite important in the sequel. But I just want to conclude by finishing the proof of the enumeration formula. Okay? So I want to understand what we actually get here. So the claim, second claim, is that so this construction is a bijection, well, so between Tn and the set of quadrangulations. So at this time, it cannot be quite true because Tn, you see, is enumerated by the number of plane trees. So this is plane trees. And I want to add the labels on top. But in order to do that, I have no choice for the root, and I have 3 choices for every edge. Okay, starting from any vertex, going up, I can only add +1, subtract 1, or add 0. Okay, so I have 3 choices for every edge. So I get a 3 to the n. So these are the labels. Okay, so it cannot be quite a bijection so far. Okay. So what I need to do is to consider really the set of quadrangulations with a distinguished vertex. So I want it to consider rooted and pointed quadrangulations with n faces, where by pointed I mean that one vertex is distinguished. And you see that actually that's what the construction does. Okay? In the end, certainly this vertex V star plays a role different from the others. And I didn't actually say how I rooted the map. Okay? But the thing is that since the tree is rooted, it's natural to root the map at the first edge that you draw in this construction, the one that goes from the root of the tree to the successor. Okay? Now, you see, this object has a root and a distinguished vertex, so I need to understand how many more objects I have here compared to the number of quadrangulations. But the fact is that in a quadrangulations, so if Q is in Qn, so the number of faces is n. The number of edges, well, I know that if I sum the degrees of the faces, I get twice the number of edges. But the degree of a face is 4. So I just get 4f, so 4n. So E is 2n. And by the Euler formula, I get that the number of vertices is 2 plus the 2n minus n. So it's just n plus 2. Okay? So for every quadrangulation, for every rooted quadrangulation, I have exactly n plus 2 choices of vertices to point the quadrangulation at. Okay? So that tells me that this is enumerated by n plus 2 times the number of quadrangulations. Okay? And now we are almost done, but if you remember, so if I divide, of course, by n plus 2, I have almost the formula I wanted, but I had a prefactor 2. And the thing is that in the construction that I gave here, I said that the root was going from the root of the tree to this vertex, but if you do that, you see that you cannot get all the maps. Essentially, so we will interpret the labels in the tree next time, but you see that along this edge, the labels have to decrease. So it seems that I have introduced a bias by doing that. So in fact, I must keep a choice of orientation for the root vertex of the map. And so really, I have to somehow choose a choice of orientation for the root of Q. Okay, and that gives me the extra factor 2. Okay. Okay, and I get the enumeration formula. Okay, so of course, you know, it's maybe this last bit about the choice of orientation was not very convincing, but next time we are going to see that the labels given by this bijection, you know, in the end, I get more than a quadrangulation. I get a quadrangulation with labels. And since I claim that this is a bijection, the labels must be a function of the map itself. Okay? And we'll understand, we'll see next time that this function is gives the graph distances to V star. Okay? And that explains why, you know, once you have V star, you determine the labels, and you really don't want to bias by taking only the roots which go from which are further away to V star and that go closer to V star. Okay, so you really need this factor 2. Right. So sorry for going over time, and so next time I want to spend, I think, 10-15 minutes on, you know, actually this claim. The other one would take a longer time, and explain the converse construction. Okay, and then okay, I think I'm going to spend some time on the so-called local limits of maps, which are maps that are defined on the infinite maps defined on the whole plane rather than the sphere, and then we'll explore the scaling limits. Okay, thank you very much.
Questions? Time for lunch? Okay, I hope everyone knows what they're doing or not doing.